Hi, this is Saik Hussain and I'm going to present the topic ECMSRC. This is a sparse learning approach for the prediction of extracellular matrix proteins. The contents we will be covering in this presentation. First of all, we will be discussing about extracellular matrix proteins, the literature review, the proposed approach, followed by the evaluation parameters, the dataset we have used in the research work, the results and comparison, and finally the presentation will be ended in conclusion. Now let's talk about a bit about extracellular matrix proteins. The extracellular matrix is a dynamic physiologically active component of all living tissues. In addition to providing the structural support for the cells embedded within a tissue, it is also a key factor in determining the functionality of the tissue. The ECM is made up of proteoglycans, water, minerals, and fibrous proteins. A prediction of where a protein resides in a cell is subcellular localization, and in general it is of imperative significance. Any meaningful study on unknown proteins cannot be achieved by overlooking the subcellular localization. Researchers have therefore been focusing on computational approaches for the identification of the problem. Since the ECM proteins are closely related to secretory proteins, it is natural to focus on secretory proteins to explore the extensive properties of the ECM. So far, a lot of work has been done in this area. The ECMPP can be regarded as the first predictor designed for the prediction of the ECM proteins, and in this particular approach, the ECM proteins are represented by augmenting 5 novel sequence-based features with 91 commonly used features. Another one is ECM-PRED, which used the random forest approach, where proteins are represented by sequence-derived features such as the frequency of amino acid or amino acid groups and physiochemical properties. Now our proposed work is basically ECMSRC to predict the ECM proteins. We propose to use the minimum redundancy and maximum relevance MRMR method for the selection of the most significant sequence-derived features. At the prediction stage, we propose to use the state-of-the-art sparse representation classification (SRC) algorithm using the overcomplete dictionary matrix of training sample. We will show that the proposed algorithm outperforms the ECM-PRED approach on a standard dataset. We have basically proposed a modular approach to achieve this. First module will be consisting of the selection of most significant features using the concept of MRMR, which I discussed earlier. The second module performs the classification by developing an overcomplete dictionary matrix of the training samples using only the discriminant features selected by the first module. Mutual information and simultaneously optimizes the minimal redundancy and maximal relevance criterion to select the M most significant features. Given the two random variables x and y, the mutual information between x and y can be defined as the following equation. In these equations, the f of x or f of y and f of x comma y denote marginal and joint distributions respectively, whereas in the third expression, the function d being the Kullback-Leibler distance between the two probability mass functions. The I of xy is a measure of the information y contains about x and therefore is an index of dependence. Consequently, mutual information is 0 if and only if x and y are independent. Mutual information gives a sense of similarity between the features. The concept of minimal redundancy feature selection is primarily to select the features that are mutually different. Now let there be a total of n number of features, psi I, psi 1 to psi n, and our problem is to find find the m most significant features, and of course m must be greater than n, lesser than n. So let omega be the set of the selected m features with the cardinality of omega is mod of omega. Then the minimum redundancy condition can be stated by the following equation. The relevance of a given feature psi I for the classification is given by the mutual information between the psi I sample and C, where C is the class vector consisting of class labels for all the training samples. Consequently, the greater the value of I function for a particular feature, the more relevant the feature is for classification. The MR-MR approach of feature selection is to simultaneously optimize the criteria in the given equation, that is max v1, and the previously discussed equation. So by combining them to yield a single optimization problem, the two most prevalent methods to achieve this are to either use the difference or the ratio of the maximum relevance and minimum redundancy criteria, which can be seen in the last two equations, that is max of v1 minus ui, vi minus ui, and max of vi upon ui. Now, after selection of the m most significant features, our ECMSRC uses the concept of sparse representation of the ECM proteins classification. Formally, we label ECM proteins and non-ECM proteins using the class index k, such that k is equal to 1 and k is equal to 2 correspond to ECM and non-ECM proteins respectively. Let there be n training samples of both the classes such that xp of k belongs to R, which has a dimension of q by 1, represents the pth training sample from the kth class with q numbers of features. We form a dictionary matrix D belongs to the dimension of q by 2 and to n by concatenating all the training samples. If a given test sample y belongs to the kth class, ideally all entries of the vector alpha are 0 except alpha 1 of k, alpha 2 of k till alpha n of k. Now the sparsest alpha can be sought through the solution of the optimization problem. In the first equation, it has been seen that it is taken the L naught norm of alpha, and the problem arising in this equation is generally a non-convex and NP hard. So to cater the issue, we can see in the second equation, which is a basis pursuit algorithm. For instance, it makes use of the L1 norm to solve the convex optimization problem. Under certain conditions, on the isometry constant of the matrix D, the sparse vector alpha can be safely recovered using the BP algorithm, basis pursuit, and ideally speaking, alpha will have high value entries corresponding to the columns of D that are relevant to the class label of the probe Y. The embedded information about the class label of Y can be used to identify the Y. Where the vector del k has all 0 entries except at the locations correspond to class k, where the value is 1, the decision is ruled in favor of the class with the minimum reconstruction error. The evaluation parameters which has been used in this work is basically the receiver operating characteristics curve, ROC, true positive rate, sensitivity, true negative rate, specificity, area under the curve, AUC, Matthews correlation coefficient, MCC, and the Udin's index. The dataset we have used so far contains 17,233 metazone secreted protein sequences obtained from Swissport release 67. Out of these sequences, 1103 sequences are ECM proteins with the class label k is equal to 1, and the remaining 16,130 proteins are secreted proteins without ECM annotation with a class label k is equal to 2. Non-redundancy was ensured by allowing a sequence identity between any two proteins of not more than 70%. The final dataset consisted of the 445 ECM proteins and 4,187 non-ECM proteins. Out of 445 ECM proteins, 300 were randomly selected to form the training data of ECM proteins, while the remaining 145 proteins were designated for testing purpose. Similarly, for the case of non-ECM proteins, 300 were randomly chosen for training, while remaining were used for testing phase. Now we can see the result over here. We can see the ROC curve, ROC characteristic curve of the ECMSRC using the top 29 features is shown. The ECMSRC achieved a high area under the curve AUC of 0.8671, which is significantly better compared to 0.7900 reported for ECM PRED. Now in this table, on the most left column, these are the methods listed which we have compared our research work, that is a J4.8 BiSNAD, AdaBoost, decision table, logistic, polynomial SVM, MLP, ECM PRED, and finally our proposed work, ECMSRC. We can see on the second column the feature subset. All of the algorithms have utilized 40 features, but over here we have utilized only 29 features. The sensitivity we have achieved so far is 74.48%. Specificity is 81.31%. MCC score is 0.256. Udens index is 0.5579, and test accuracy is 81.06%, which can be seen that all the parameters we have achieved so far are greater. So we can say that our algorithm has outperformed all the discussed algorithms in this table. So finally, we are going to conclude the presentation with our final remarks. Now it is imperative to develop machine learning algorithms for accurate and expeditious prediction of the ECMs. We proposed a novel approach for the classification of the ECM and non-ECM proteins called ECMSRC. The most representative features in an information theoretic sense are chosen by employing the MR-MR approach. In particular, we report a test accuracy of 81.06% with 0.5579 Udens index by making the use of only 29 features. The proposed algorithm outperforms the ECM PRED methods by a margin of 4.06% and 0.1379 in test accuracy and Udens index respectively. The proposed ECMSRC algorithm utilizes fewer features compared to ECM PRED. 40 features they have used to achieve this superior performance, and we report a 80% verification rate for the proposed ECMSRC algorithm, which is 5% higher than the ECM PRED method. So finally, these are the final remarks, and I am concluding this presentation. Hope you all like it. Thank you so much. Have a nice day.